3D equilibrium of forces using Casio FX-570ES or 991ES Plus 2nd edition. In this example, we have a flower pot, 40 kilograms, that is supported by 3 cables as shown in the figure. We are asked to determine the tension in the cables AB, AC, and AD using equilibrium equations. Now, first step is to draw the free body diagram of the system. So as you can see here, we have the weight of the flower pot, which is 40 kilograms. Multiplying that by 9.81 gives us the weight in newtons. Next, we have 3 cables here. By drawing the tension forces on the 3 cables, so we have for AB, we have for AC, and we have for AD. Since they are tension forces, the direction is always away from the point to which it is applied. Next, because force on AD is diagonal, we will get the coordinates of points A and D. So for point A, it's 1.5, 2, and 0. And then for D, we have 0, 0, and 1.5, which can be determined through inspection. And once we determine the coordinates of A and D, we can now get the radius vector of the force of AD. So to do that, we will plug in the values square root of the parentheses, and then what we will do is to subtract the final and the initial point component by component. So in this case, since A is the initial point or the tail of the force, and D is the final point or the head of the force, so we will do the final, which is point D, minus initial, which is point A, component by component. So let's start with the x coordinates. So for D, it is 0. And then for A, it is 1.5. So 1.5 squared. And then next is for y coordinates. For D, it is 0. So let's add plus, parenthesis, 0. Minus initial, that's point A, so 2 squared. And then finally, we have parenthesis. And then for the z coordinates, so final point D, 1.5. Minus initial, which is 0 for point A. And then squared. So once we input that formula, let's press Shift, Store, and then Hype key to store it to variable C as shown. So we now have this input and stored to variable C. We'll use that later. Next, let's set up the equation since this is a 3D equilibrium problem. So we will have a system of 3 equations in 3 unknowns based on equilibrium equations. So let's go to mode and then 5, so the equation mode. And then we have lots of options here to choose depending on what type of equation it is or what system it is. But for this problem, we will use option 2 for 3 linear equations and 3 variables. So option 2, it is. Now we have this table. So the headers A, B, C, and D will be represented by these headers in the real life problem. So for header A, so that will be the force on AB, component by component. For header B, so that's the force on AC. For header C, that's the force on AD. And for the header D, that will be represented by negative of W. Negative W because it's initially plus W on the left side of the equation. We transpose it to the right, so that becomes negative W. D is the constant. Next, the rows, row number 1, 2, 3, represent the equation in itself. So the first row is the summation of forces horizontal, or X. The second row is the summation of forces Y. And the third is the summation of forces Z. So we do it row by row in this case. Let's start with header A, or the components of the force AB. Notice that force AB is parallel to the Y direction. So in terms of components, only the Y direction has a non-zero value. The rest of the components, the X and Z components, are considered as 0. So in this case, we will set the y equation, so which is the Fy by 1 for force AB, and then the rest is 0. Next, for force AC, notice that it is parallel to the x-axis. So in terms of components, only the x component has a non-zero value. The rest, which is y and z, are considered 0. So in this case, the rho for x is 1 for force of AC, and then 0 for the other components. Finally, for force of AD, since it is diagonal, it is not parallel to any of the axes, so we will calculate the coefficients of its unit vector, or the components of the unit vector. So to do that, first, for the x component, we will get the final x component, so in this case D, minus the initial x component, in this case A, so that's 0 minus 1.5, and then we divide that by C, which is the square root expression we calculated earlier. So to do that, and then for the y component, so we do the same. We subtract the final y component, and then to the initial y component. So in this case, 0 minus 2, and then we divide that by C again. And then finally, we subtract the final z component to the initial z component, so 1.5 minus 0, and then we divide that again by C. So let's input that. 0, 1 equals, and then 0 minus 1.5 over C, so alpha C equals, and then 1, 0, and then 0 minus 2, here minus 2 divided by alpha C. Then next is 0, 0, and then 1.5 minus 0 over alpha C equals, okay. And then for the column D, or column negative W in this problem, notice that the weight of the flower pot is directed downward and parallel to the Z direction. So in terms of components, we only have the Z component. The rest is considered 0. So we have the X component, which is 0, and then Y component is 0, and then for Z, since negative W, so we have negative of negative 392.4. So negative 392.4, because the weight is downward and positive Z is upward, so it is negative in value. So we have on our D row, so 0, 0, and then for the third row, we have negative of negative 392.4 equals. Now, once we have inputted the entire expression, we can now press equal sign to get the final answer. So for X, we have 523.2. Since we set the first column for force of AB, so that is the X value, and therefore FAB is 523.2 newtons. For the Y value, press it one more time, so you will get 392.4, and since we assign the second column for AC, so that is the value of Y. So in this case, FAC is 392.4 newtons. Finally, pressing equals one more time, you will get the value of Z, which is 762.69 newtons. And since we assign the third column to force of AD, then that is the Z value. So in this case, FAD is equal to 762.69 newtons. And we have now the final answer for this problem. So that's it for the equation mode using the Casio calculator. So that's it for our video. I'm Engineer JD, and see you on the next video, mga Casio Nation.